Alright, so what we have here is a system where we have a 3 kilogram cart. So the mass of this cart is 3 kilograms. It's not the weight of the cart, it's the mass of the cart. Kilograms are units for mass. So we know that the mass of this cart is 3 kilograms. And we also know that these weights have an equal mass and therefore have an equal force of weight. If we were to draw a free body diagram for each of these weights, we would have two forces. We would have the force of weight pulling the object down, applying a downward force, and you would have a force of this rope or string pulling the object up. Now, the force that always pulls objects down, the gravitational force, is what we call the force of weight. And the force of a rope or string pulling on an object is called tension. So we have two forces acting on these weights, the force of weight and tension. Anyway, number 1A wants to know how many normal forces are acting on the cart. Well, technically speaking, normal forces are the forces that a surface applies to an object. So we have 4 normal forces here. We can only really see 2 of them, but there's a normal force being applied to each of these wheels. And the cart's going to have 4 wheels, but we can, like I said, we can only see 2. So we have a normal force here, normal force, and a normal force here on the cart. So how many forces does the cart have? Technically speaking, 4. Draw the normal forces on the cart. Well, we did that. The normal force is being applied upwards because the normal force is always perpendicular to a surface. So the cart is on the table and the force of weight is being applied downward to the table, so the normal force is going to be applied perpendicularly, so it's going to be applied up. Okay, so that's why our arrows are pointed up. So we drew our normal forces. Can check that off. How many normal forces are acting on the hanging masses? Well, these masses are hanging, so since a normal force is a force that surfaces apply, these masses actually have no normal forces, so there are none. Now, what force is acting on all the cart and the masses? Well, this system happens to be on Earth, so we have the force of weight. Calculate the force of weight of the cart. Well, we have a nifty equation for force of weight. The force of weight is equal to mass times gravity. The mass of the object is 3 kilograms, and the gravity on Earth, because this is on Earth, is, we're going to use 9.8. Some of you will use 10, but we're going to use the magnitude of gravity, so it's going to be positive. When we multiply these out, we get, let's grab our calculator, turn it on, 3 times 9.8, and we get 29.4. So this is actually 29.4, the units for force are newtons, and it's actually pointing down because the force of weight is always down. So it wants to know in 1F, if the cart is moving, is it accelerating or at constant speed? Well, let's think about this. The force of weight are equal on both sides. Therefore, our net force is 0. So the sum of our forces is 0 newtons. Now, if we're following the equation force equals mass times acceleration, we have a force of 0. That's our net force. times our mass, which is 3. So what is our acceleration going to be? If our force is 0 and our mass is 3, acceleration has to be 0 as well, because 0 times 3 is going to give us 0. So we know that this object is not accelerating. So if the cart is moving, is it accelerating or at a constant speed? It's going to be at a constant speed. Just because the net force is 0 doesn't mean that the cart is at rest. Now it could be at rest, but it could also be moving with a constant speed. Right? Your velocity could be constant since you don't have an acceleration. So 1g asks why. Well, it's because our net force is 0, and since the force equals mass times acceleration, our acceleration has to be 0.